Hello, this is not your Ken tutor, and in this video, I will teach you how to solve the molar mass of an ideal gas. As usual, I included examples at the end of the video so we can practice some calculations. Usually, in general chemistry, you will encounter two cases where you are asked to solve for the molar mass. For the first case, the problem will give you the density of the ideal gas. If that's the case, then you will use this formula. Capital M, which is molar mass, is equal to ρ. This Greek letter ρ stands for density, times R, which is the gas constant, times temperature divided by pressure. Now, in my previous video, I discussed the density of the ideal gas, and this formula appears in that video. So if you want to learn more about getting the molar mass of an ideal gas if given the density, then you should check out that video. I will put the link on the description box. Because in this video, we will be focusing on the second case, which is solving for the molar mass if given the mass of an ideal gas. Now, if this is the case, you will use this formula. Capital M, of course, is the molar mass. Lowercase m or small letter m is the mass. R is gas constant. T is temperature. P is pressure. And V is volume. Now, in this video, we will be using the gas constant 0.0821 liter atmosphere per mole Kelvin. So if you use this gas constant, make sure that your temperature is in the unit Kelvin, your volume is in the unit liters, your pressure is in the unit atmosphere. Of course, the unit of mass is grams. So the unit for the molar mass, if you cancel the units in the formula, what is left is grams per mole. So the unit for molar mass is grams per mole. Now, if you're wondering how we derived this equation for the molar mass, I'll show you quickly how it was derived. So in deriving this equation, we start with the ideal gas equation, PV equals nRT. Now, we know that N stands for the moles of the ideal gas, and we know that moles, or N, is equal to mass divided by molar mass. So, lowercase m divided by capital case M, mass divided by molar mass. Then we will plug this into our equation. So PV equals N, and N is equal to mass divided by molar mass, RT. Now, if we cross multiply, this becomes capital M PV equals small m RT. Now, if you divide both sides by PV, PV will cancel on the left side, and therefore, your equation becomes capital M is equal to mRT over PV, which is the equation we have below. So this is how the equation was derived from the ideal gas law. So for example 1, at 720 torr and 30 degrees Celsius, a gas weighing 6.08 grams occupies a volume of 4.00 liters. What is the molar mass of the gas? So if we assume ideal conditions, we will be using the formula we just learned a while ago, which is this one. M is equal to mass times RT divided by PV. Now let's substitute the values. So M is equal to the mass of the gas is given in the problem, which is 6.08 grams. So 6.08 grams. R, of course, is the gas constant. We know that 0.0821 liter atmosphere per mole Kelvin. T is the temperature, and remember, the temperature must be in Kelvin. And the given in the problem is 30 degrees Celsius. So we need to convert this first into Kelvin. Remember that when you convert degrees Celsius to Kelvin, you simply add 273.15. So 30 plus 273.15, that is equal to 303.15, and the unit will be Kelvin. So this becomes our temperature. Divided by the pressure, and the unit must be in ATM. In our problem, the given temperature is 720 torr. So we need to convert that into ATM. If you have watched my video about converting units of pressure, you know that 1 ATM is equivalent to 760 torr. So torr will cancel out, and what is left is ATM. So 720 times 1 divided by 760, that is equal to 0.947 ATM. So this will be the pressure. If you want to learn more about converting units of pressure, you can check the link I put on the description box. And then our volume must be in liters, and what is given in the problem is 4.00 liters. So let's see how the units will cancel out. Liters will cancel, ATM will cancel, Kelvin also cancels. So what is left is grams per mole, or grams over mole. And if you solve this in your calculator, 6.08 times 0.0821 times 303.15 divided by 0.947 times 4, this is equal to approximately 39.95 grams per mole. And this is the answer to the question. For our second example, at STP, a 0.556 liters of a gas weighs 0.500 grams. What is the molar mass of the gas? Now, if we assume ideal conditions, again, we will use this formula. Now, if you read the problem, it says there at STP. In my previous video, I explained what STP means. STP means standard temperature and pressure. And the standard temperature is 273.15 Kelvin. And the standard pressure is 1 ATM. Now, if you want to learn more about STP, you can check the video using the link on the description box. Now, let's use the formula. Molar mass is equal to M, which is given in the problem, 0.500 grams. R is the gas constant, 0.0821 liter atmosphere per mole Kelvin. And T is the temperature, which is the standard temperature, 273.15 Kelvin. Divided by the pressure, which is the standard pressure, 1 ATM, times the volume given in the problem, which is 0.556 liters. So again, ATM will cancel, liters will cancel, Kelvin will also cancel, so the unit of molar mass would be grams per mole. Now, if you solve this in your calculator, we have 0.5 times 0.0821 times 273.15 divided by 1 times 0.556. This is approximately equal to 20.17 grams per mole. This is the answer to the question. For our last example, what mass of carbon dioxide occupies a volume of 1 liter at 0.987 atm and 25 degrees Celsius? So in this problem, we are given the molar mass and it is asking for the mass of the gas. So we can still use this equation. However, we need to rearrange it. So molar mass is equal to mass times RT over PV. What you can do is you can multiply both sides of the equation by PV. When you do that, PV cancels on the right side. So what remains on the right side is MRT. On the left side, we have pressure times volume times molar mass. If you want to solve for the mass, you will divide both sides by RT. So RT will cancel on the right side. So what is left on the right side is mass. And on the left side, we have pressure, volume, molar mass divided by RT. So we will be using this formula to solve for the mass of the ideal gas. So mass is equal to P is pressure, and according to the problem, that's 0.987 atm. V is the volume. According to the problem, that's 1 liter. M is the molar mass, which is 44.01 grams per mole, divided by R, which is 0.0821 liter atmosphere per mole Kelvin, times T, which is temperature. The given is 25 degrees Celsius, so we need to convert that into Kelvin. Again, you just add 273.15, and that's equal to 298.15, and the unit is Kelvin. So let's see how the units will cancel out. ATM will cancel. Liters will cancel. Moles will also cancel, and Kelvin will cancel. So the remaining unit is grams, which is the unit of mass. And if you solve this in your calculator, we have 0.987 times 1 times 44.01 divided by 0.0821 times 298.15. This is approximately equal to 1.77 grams. And this is the answer to the question.